We're gonna take a look at something called partial derivatives. You know what a derivative is, but what does it mean for it to be a partial derivative? That's what you're going to find out. We're going to take this function here. Notice it's a function of two variables. By the way, for simplicity, let us just write f instead of f of xy. It's clear that f is a function of x and y anyway, so no need to overtly state that. What does it mean to take a partial derivative? Well, as you'll recall, a derivative in general is a rate of change. A partial derivative of a function with respect to one of its variables is the rate of change with respect to that variable, assuming all other variables are held constant. More later on what it means to hold a variable constant. This is the symbol we use for the partial derivative with respect to x. Notice the d's have a little curly tail on them, as opposed to just an ordinary d that you might see in a regular derivative. These are not the same thing. So what we're going to do here is I'll show you how to differentiate this function with respect to the variable x. The first thing we know about derivatives is that they can distribute to a sum or difference. This is also true for partial derivatives. Let's go through each term here and see what the partial derivative would mean. For this first term, the partial derivative means that any variable that isn't x is being assumed to be constant or held constant throughout the differentiation process. Well, in this first term, there are no y's. There are no variables other than x, and therefore the partial derivative is the same as the ordinary derivative. The second term here, however, has a y in it, but we're differentiating it with respect to the variable x. That means that we are to assume, for derivative purposes, that y is a constant and not changing. If we're assuming y is a constant, then think of this. Isn't 4xy cubed the same as this expression? Notice I've just rewritten it so that it's a constant times x. But isn't the derivative of a constant times x just that constant? After all, the derivative of 17x is definitely 17, so the same logic would apply to any other constant multiple of x here. You'll notice again in that next term that we assumed y was a constant when calculating the partial derivative. The next term doesn't have any y's in it, so the derivative of 6x is just 6. The same is true for partial derivatives. In regard to this next term, that term has a value of 0. Why? Because we're assuming that any variable that isn't x is a constant. Therefore, 2 times a constant is a constant, and the derivative of a constant is 0. Likewise, the derivative of 10 is 0, so I won't add 0 onto our answer twice, and that completes the partial derivative process. By the way, it's worth noting that partial derivatives can be written with curly d's. They can also be written with just the function name and a small x as a subscript to represent the variable of differentiation. Note, this is not the same as when we say f of x. When the x has no parentheses and is a subscript, it indicates that we took a derivative with respect to that variable. To get a little bit more sense of what a partial derivative actually means, let's think about the rate of change of this function with respect to x for some constant value y. That is what we just calculated. For this, we'll ask the question, how fast is f changing with respect to x when x is 3 and y is 1? Remember, since we're calculating a partial derivative with respect to the variable x, y is assumed to be constant. Here's the partial derivative we got earlier when we calculated it. Now, while it's clear that y is a constant because they've told us y is 1, wouldn't that mean that them telling us that x is 3 is also assuming that x is a constant? It might sound that way at first, but let's add some nuance to this discussion. First of all, we'll calculate the partial derivative by plugging in 3 and 1. And when we plug those in, we get 4. But what does it mean to say rate of change with respect to x when y is constant? It seems like they've given us constants for both of them. So what does this 4 mean? Well, it means what any derivative with respect to x would mean. You may recall, going way back to the beginning of Calculus 1, that when a derivative is 4, that means that small changes in the variable will result in 4 times those changes to the overall function. That's precisely what a derivative has always meant when a derivative is 4. It means when x changes a little, the function changes by 4 times that little amount, or approximately anyways. Now, to get a more sense of what this means, I'm going to show you something here. Suppose we plugged in 3 and 1, which are the x and y values at hand here. But then suppose we plugged in a slightly larger value of x, say 3.2 instead of 3. This is what we mean by small changes in x. Well, I'm assuming that since we have a small change in x, we should have 4 times that amount of change in the function value. Let's do some actual calculation here. Notice that x changed by 0.2 while holding y constant at 1. The function went from 15 to 15.84. That's a change of about 0.8, technically 0.84, but I'm just trying to give a rough sense of an approximation here. And you'll notice that this small change in x led to a 4 times that amount of change in y. Why does this not work exactly? How are we dismissing the 0.84 change in the function value as opposed to, and by calling it 0.8? Well, remember, these aren't really meant to be literal. They're meant to be instantaneous rates of change when x is 3. The minute x is no longer 3, the instantaneous rate of change changes a little bit and makes this not a precise science. But it does give you a sense that the change in f was about 4 times the change in x, and that lets you know what the derivative of 4, the derivative value of 4 actually means. This symbol here for the partial derivative, which can also be written this way, could also be taken with respect to other variables such as y. We didn't do the partial derivative with respect to y here, but I didn't want you to think there was something special about the variable x. We can take partial derivatives with respect to any variable in the function we want. Now, let's take a look at this same function. Here's the derivative with respect to x that we found earlier. And let's talk about symbols. These two symbols, you want to get loose about being able to interchange those in your own mind. They both mean the partial derivative with respect to a function. That being said, let's take a look at what we mean by a second-order partial derivative. You'll remember back in calculus that there was such a thing as a second derivative. Well, the same thing is true for partial derivatives. So remember the derivative we took earlier with respect to x? We could take the derivative of that derivative with respect to x. I'll do that work in just a moment. Or that same first-order derivative with respect to x that we took earlier, we could differentiate that with respect to y. I'll do that work in a moment. But notice for these two problems I'm about to do, I'm differentiating with respect to different variables. So on the left, when I take the derivative, I'm assuming y is a constant. Whereas on the right, when I take the derivative with respect to y, I'm assuming that x is a constant. So on the left side of the screen, that derivative would be 2, and on the right, that derivative would be 12y squared. I recommend hitting pause and letting your brain process this. And finally, some symbol notation. When we take the derivative with respect to x twice, we often call that by this set of symbols, or even just fxx, to represent differentiating twice with respect to x. On the right, when we differentiate with respect to x once and then y once, we often write that partial derivative this way, or for simplicity, just fxy, meaning we've taken the derivative with respect to x, taken that answer, and then differentiated with respect to y. And those are the notations that we'll use going forward.